Iodine deficiency is a global health problem that affects roughly 2 billion people per year. The deficiency primarily affects individuals living in developing countries, however, it has been prevalent and well developed in iodine-sufficient areas. In pregnant women, a deficiency in iodine is seen significantly due to the increased iodine requirement needed to benefit both the mother and fetus. A significant iodine intake increase of roughly 50% is required by pregnant women due to an increase in renal iodine excretion, increased production of thyroid hormones, and fetal iodine requirements. Iodine is an essential micronutrient needed in the synthesis of thyroid hormones, which are crucial for metabolism and proper development of the nervous system. It is also fundamental to the growth of a healthy brain. Women who are vulnerable to a deficiency in iodine are at risk of death, miscarriage, stillbirth, and hypothyroidism, and if the child is born, the child may suffer from impaired cognitive development and learning capabilities, as well as delayed psychomotor development among other deficiencies due to hypothyroidism. Thyroid hormones play fundamental roles in the development and maturation of the brain. A fetus is dependent on maternal supply of these hormones because it does not begin thyroid synthesis until the middle period of gestation. The consequences of severe maternal thyroid hormone deficiency due to a lack of iodine and its neurodevelopment is well established and studied. Severe iodine deficiency, even very mild in manner, may cause maternal hypothyroxanemia, which is related to cognitive and psychomotor deficits. These observed adverse effects on fetuses, infants, and children of mothers with mild to severe iodine deficiency are reported to be irreversible after birth. Therefore, it is important to become knowledgeable of the role of maternal thyroid hormone dysfunction due to a lack of iodine plays in the neurodevelopment of the fetus in terms of magnitude, time sensitivity, and nature. Different tissues throughout the body modulate the impact of circulating thyroid hormones through their needs via 3 iodothyronine dehydrogenases called D1, D2, and D3. D1 is specific to the conversion of T4, thyroid hormone thyroxine, and the inactive thyroid hormone, to T3, triiodothyronine, the active thyroid hormone. D1 is also responsible in recycling iodine from inactive iodothyronines. Placental D3 may also provide the fetal thyroid with recycled iodine from iodothyronine metabolism. Consequently, maternal thyroid hormone, specifically T4, is important in supplying the fetal cortex with thyroid hormones beginning early in pregnancy. In order to maintain stable levels of T3 and 4 throughout the body to the needs of the individual, maternal thyroid hormone production increases by 50%. The increased need for iodine occurs for various reasons, such as increased synthesis of thyroid hormones by the maternal thyroid gland, increased renal clearance of iodine, and the transfer of iodine to the fetus to promote fetal thyroid development. HCG hormone produced during pregnancy also stimulates the transfer of iodine across the placenta. In summation, insufficient iodine intake leads to overproduction of T3 and T4 in order to conserve any amount of iodine within the body. This then leads to low levels of free T4. Because T4 is the primary hormone delivered across the placenta to the developing fetus, fetal neurodevelopment may be adversely affected. The most vulnerable groups of individuals at risk for iodine deficiency are pregnant and lactating women and the fetus. Not only is iodine deficiency prevalent in developing countries, it has become increasingly widespread in many Western nations that were once considered free of iodine deficiency. A possible reason for this change could be diet changes such as consuming more processed foods, which are prepared with non-iodized salt. Of the world's population, 2 billion individuals are affected, with those who are African making up 321 million of the individuals most at risk for insufficient iodine intake. From reports of global data, Ethiopia is considered moderately iodine deficient. Ethiopia is a country which has one of the highest prevalence of iodine deficiency and has the worst programs to prevent it. Another significant area of iodine deficiency is in China, where the soil and universal drinking water contain very little iodine. In the 1980s, it was reported that nearly 12 million individuals were at risk for iodine deficiency, and nearly 500,000 schoolchildren were presenting signs of goiters. In a study conducted in a province in China, researchers recruited participants from the 8 surveillance counties located throughout the province between April 2014 and September 2015 and found these women to be iodine deficient. These areas are highly known to be impoverished and remote, and previous cretinism or iodine deficiency was known to have occurred. 1,370 pregnant women participated. A 20 milliliter spot urine sample was collected, as well as 50 grams of household table salt. The median UIC of the total study population was 129.34 micrograms per liter, with the optimal level being 150. Astonishingly enough, it was found that of the 1,304 salt samples, 1,234 were iodized, suggesting that although iodization of salt was implemented, pregnant women were still not obtaining enough iodine to be optimal. A second reason for this was found to be the drinking water. The iodine concentration was less than 100 micrograms per liter, suggesting that it was not optimal. Iodine deficiency has become so prevalent that its impact has resulted in various programs and policies. One reflection is in initiatives such as World Health Organization's salt iodization program. Another is the Newborn Screening Program, which tests for congenital hypothyroidism. Both of these programs are now considered standard practice in various parts of the world. WHO also recommends an analysis of urinary iodine concentration via urine samples in order to assess the iodine status of the population. In summation, iodine is significantly important in the production of thyroid hormones, which are transferred from mother to fetus during pregnancy. Insufficient iodine intake may result in improper neural development in the fetus. It can also lead to miscarriage, stillbirth, or even the death of the mother. If birth is given, it may result in irreversible effects such as impaired cognitive development, impaired learning, and delayed psychomotor development. Initiatives such as WHO's salt iodization program, as well as regular testing of UIC levels within a population, have been implemented to address this issue.